Good morning. I'm Enis Çetin. I'm on leave from Bilkent University, currently with the University of Illinois at Chicago, and the other authors are with the Middle East Technical University. Um, I couldn't get a visa on time. That's why I prepared this YouTube video clip. Non-Euclidean vector product for neural networks. In this talk, we'll introduce a multiplication-free operator, and based on this operator, we'll have a vector product, and we will use it to develop additive networks. And I'll present some of the properties of additive networks, and I'll present our experimental results in CFAR and MNIST datasets, and I have some conclusions. Now, it's well known that convolutional neural networks are computationally expensive, and you need to perform tens of hundreds of millions. You need to perform a lot of multiplications to process a typical image, and multiplications consume energy. So we have this additive operator, and we want to replace the multiplications by an additive operator, and it turns out that this operator leads to a vector product which is related with the L1 operator. So this AddNet is an energy efficient neural network. So here's the definition of the multiplication-free operator. Let x and y be two real numbers. The operator is defined as x, quote unquote, plus y is sine of x times y, absolute value of x plus absolute value of y. So if I have minus 3 and minus 7 here, my result would be plus 10. Okay, the sine of x times y is plus 1, and absolute value of 3 plus absolute value of 7 is plus 10. So this operator can be also written as sine of x times y plus sine of y times x. And it does not require any multiplications. We call it the multiplication-free operator, and we can easily extend it to vectors. And so if x and y are two vectors, then we can define this vector product, quote unquote vector product, as summation sine xi yi, absolute value of xi plus absolute value of yi. And this operator is related with the L1 norm. So if you have x plus x, you get 2 times the L1 norm of x1. So in a way, it induces the L1 norm. And it can be considered as, if this vector product can be considered as a special case of correlation operation between the two vectors. So we can use it in neural networks. Okay, that's the idea. And I have here two graphs. So if you have x times y between minus 1 and plus 1, you have this curve. And if you have our operator, you have some discontinuity. So that's the bad side of the operator. It's computationally efficient, but it's not smooth. So as I just pointed out, if I have the dot product of x and x, we get 2 times the absolute value of 2 times the L1 norm of x. So how do we define the AddNets, additive neural networks, using this multiplication operator? So you have this typical neuron. The input values are x1, x2, all the way up to xm. And I have here the bias bk. So, and the weights wk1, w through wkm. We have the summing function, summing operation, and then we have the activation function. So we replace the multiplication by our operator, and that's basically it. So we get a new neural network operator. Actually, you don't need this activation function, or you may not need the activation function. You can design neural networks without the activation function, because the operator is a nonlinear operator. But we will be using ReLU in our networks. So we'll be using ReLU, and we may need to modify the slope of the ReLU function. So the modified equation will be this one. Okay, so okay, I had a typo and I corrected it. This is the scaling factor which changes the slope of the ReLU. And so actually we perform a multiplication, one multiplication in each neuron. Okay, so the AddNet is not totally multiplication free, but we perform one multiplication in each neuron, and we learn these weights during batch normalization. So I have to talk about the training operation. What's nice about the operator is that we can use the standard backpropagation algorithm during training, because we can compute the partial derivatives of the multiplication-free operators with respect to w or with respect to x. And it turns out that the derivative of the w times sine x plus x times sine w is just sine x plus 2 times x, the Dirac delta function evaluated at w. And obviously the derivative with respect to delta x is the dual of this top derivative. And delta is the Dirac delta function, but having w is equal to 0 or x is equal to 0 are events with zero probability, or they have zero measure, so they cannot happen in practice. So we can omit the Dirac delta function in practice, and we can approximate the derivatives by the signs, sine of x and sine of w. So the derivative is +1 or -1 basically. And we use these derivatives in backpropagation algorithm. They can be generalized to vector and matrix operations, but the convergence is slower than the regular neural network. So we studied the MNIST data set and the CFAR. So let's first start with the MNIST data set. As you know, there are handwritten digits, and the image sizes are 28 by 28. And we basically compare the AddNet with ordinary neural networks. So we have this structure, convolutional layer 1, max pooling layer 1, convolutional layer 2, max pooling, fully connected layer, softmax layer, and in both regular neural network and the MNIST neural net, in our multiplication-free neural network. With this model, you can get 99.2% recognition accuracy using regular neurons. And in AddNet, we replace the convolutional layers with our multiplication-free operator-based layers, and it leads to we get 99% accuracy, so very close to the 99.2%. And the weights in each neuron, we perform one multiplication in each neuron. Weights are determined using the L1 norm of the weights, and then we have these H, W, and D parameters are the filter height, width, and depth. And we've also tried some other parameter estimation, simple parameter weight estimate, the scaling parameter estimation scheme, so standard deviation, etc. But this L1 norm-based normalization gave us the best result, but it requires a single multiplication in each neuron. So our result is pretty close to 99.2 in the MNIST data set. And these are the other strategies that we had to achieve this result. We used the batch of size 64, ReLU activation function. The cost function is cross entropy with softmax, and we have the momentum update rule. We may try different cost functions in the future. Now, let's discuss our results in the CFAR10 dataset. So this is a more difficult dataset, and we have the following structure, and the model architecture is described in this view graph or slide. So we have 3 convolutional layers and then 2 fully connected layers, and then the softmax layer. Here we used batch normalization during the network training. The architecture is closely related to that to the one used in binary connect with filter depth about 0.7 for each layer. This means that the number of connection is reduced to half of that in binary connect. We replaced all layers by multiplication-free operators except the last fully connected layer and the softmax layer. Then our classification accuracy over the testing dataset is 88%. If we keep 2 fully connected layers regular, then we get 90.7% accuracy. We used stochastic binarization during training. I have some other slides describing the CFAR, the details of our training in CFAR 10 data sets. And I'm running out of time. I'll just show these and jump to the conclusion that we show that in this talk, in this paper, we show that AddNet is a reasonable neural network. It provides a trade-off between binary neural networks and regular neural networks. AddNet is more energy efficient than regular neural networks because of the reduced number of multiplications, and AddNet can be used in edge applications where the energy is important. And we demonstrated that AddNets can achieve high classification or recognition accuracy on MNIST and CFAR 10 data sets. And if you have any questions, you can send me your emails at aecyy@uic.edu. And thank you very much for listening.